Here are the 4 parts of our design. After an intense group discussion, we finally choose to build a catamaran that has a higher stability and a lower resistance. The weight of electrical components are listed in the table. And here are the weights of other components. By estimating the final mass of our boat, we then know how to design our hulls. By calculation, the volumetric displacement of one hull is 600 milliliters. Here are the 3 versions of hulls. For better stability and convenience, we finally choose 4 1-liter water bottles to be our hulls. We use the formula from the supporting PowerPoint provided by Dr. Raul to measure the stability of our boat. If result GM here is greater than 0, then our boat should be stable. From modeling, we found the value of VCB is approximately 0.9 cm using the parallel axis theorem and the moment of inertia of a rectangle area. We calculated the inertia of T. From SolidWorks, we can easily obtain VCG by applying what we found out above. From the calculation, we found that the GM is much higher than 0, which implies that the double hull boat should be stable as we considered. In the experiment, we test the boat with smaller distance between 2 hulls, which leads to a lower inertia of T and an estimated VCG. The boat was stable enough. To achieve the goal of high speed, the efficient power system is almost one of the most important portions of our design. Here are the 4 steps for designing the power system in our boat. In fact, the first 3 steps are enough for getting design parameters. However, the 4th step, simulator, helps us to understand the movement of our boat, which can in turn improve our design.
Boat resistance is a force that acts against the motion of the boat. It is based on the total coefficient of friction, density of seawater, velocity, and wetted surface area of the boat. In order to obtain the coefficient of frictional resistance, there are several other coefficients we have to decide. The specific frictional resistance coefficient could be determined based on the Reynolds number, the length and velocity of the boat, as well as the density and viscosity of seawater. According to a professional document published by Gottheimer and Harvard, the residual resistance coefficient CR has been expressed as a function of front number and the speed length ratio. From referencing all the given curves, we have generated a new graph, which is based on several piecewise fitting polynomials by tracing a series of points. The result we have is when the breaststroke ratio is 2.5, so we have to apply a correction formula in order to get the true value when the ratio is 2.97. Next we have is the incremental resistance coefficient. In our case, it is determined to be 0.004 since our boat is so small that it is not applicable for using formula calculation. The air resistance coefficient is determined based on the given equation. Here's an example when the velocity is 1.5 knots per second. Recall that the total resistance coefficient is the sum of all coefficients of different types of friction involved. After plugging all the data, the total resistance coefficient shall be determined and eventually the resistance of our boat.
From the previous description, we can now write a Python script to calculate the results at a series of velocity values and draw the graph about CF, CR, RT, and PT with respect to time. The program's calculating process is totally the same as the previous example when velocity is 0.765. Here are the plots drawn by the Python program. To verify the calculation result again, we also used the free surface flow simulation in SolidWorks to simulate our boat's working condition and solve for the resistance of our boat. The result is about 1.4 newtons, which is relatively close to the result of our Python script. From the LEGO official website, we found the basic parameters of our servo model, and we calculated the output power of our boat. Also from the official website, we can have a rough calculation of battery life. By eliminating the power of EV3 brake, we finally get the result T of around 3 hours, which is more than enough to complete the game. For convenience, we assume each propeller needs to provide power of 3 watts. We then assume the propellers have the efficiency of 65%. Now we can calculate the maximum velocity of our boat, which can be used to select the most fitted propeller. From the supporting documents, we now choose to use 3-blade propellers with the blade area ratio equal to 0.5. By doing research on the different gear combination, we finally choose to use the gear ratio of 5/1. And now we can calculate the diameter of the propeller. Since we already know how the efficiency, the resistance change with respect to velocity, we can now use integral to calculate the exact state of movement of our boat at a specific time. In other words, we can predict the state of movement of our boat. We first find some points from the curve and then use the Python program to interpolate those points into curves. Then convert this into the graph about efficiency and velocity, and then into the graph about thrust and velocity. Using the basic principle in physics and integration, we got the plots about the boat's mechanics. Now we can know, theoretically, how much force exerted on the boat at each point in time. When will the boat start the planning state, or how long will the boat complete a 50 meters movement, and so on. For convenience, we choose a flat acrylic sheet as the platform for installing all the other components together. The acrylic sheet is light, easy to drill hole, and cheap. All the holes are arranged in 3D modeling to ensure enough space and a balanced center of gravity. The holes and the platform are connected by the 4 3D printed support. The hooks are designed to hook rubber bands, which help us to easily change different holes. We directly use the parts from EV3 kits to build our gearbox. The power transmission device connects the power from the gearbox into propellers. It is also directly built in Lego parts. Using Hydrocom software, we input all the calculated propeller parameters and get a SWV file. Then we import the file into SolidWorks and create the propeller's 3D modeling after a series of operations. The propellers were made by 3D printing. Then we will combine and install all parts together. Our boat is now completed.
What we are trying to accomplish is to make the boat be able to go straight and make turns. There are 3 ways to control the movement of the boat. The first one is by using the fork case. The boat can move forward and backward, turning left and right. The second method is the vector form. We apply the third method for the computation, with 2 keys to manage each propeller. We use an application called Gopher to connect computer with the Xbox One controller. Then we improve the code so that we could use the Xbox One controller to control the boat.
On this page, we have listed all the applications and documents we have referred during the process. Our total spending is about $30, which is within the 100 spending limit.
Is that all? No. In the hard work of several months, each of those complex formulas, graphs, with odd curves were time-consuming flow simulations, all reflects Gikiyin's engineers' pursuits to the goal of being extreme. After the real-world experiment of version 1, we redesigned the whole boat. If the version 1 is a little attempt to the extreme speed, the Gikiyin's version 2 eSMART boat is another bold breakthrough to the extreme. So what's new? The first huge improvement is in the aspect of aesthetics. The artists from Team Gikiyin spent a long time on the clean and graceful curve and surface design. Their hard work finally brings us a pretty product with a sense of industrial design. The original one-piece power transmission design and the brand new hull design brings us both into a lower wave making resistance and higher speed. Engineers from Gikiyin also redesigned the whole transmission system. The decrease the transmission stages in the new installed bearing boosts the transmission efficiency.